Hi, everyone. It's the first talk after lunch. It's nothing better than combining microwave and optical systems. I mean, you can see it from the title, it's quite broad, so I will not talk about all of those areas. The quantum sensing is just a sort of motivation for you to convince you why nonlinearity in quantum mechanics is actually very important. So in my team, we do a lot of research in different areas. As you can see it, it's quite broad. In principle, I'm working the boundary of micro and optic in my team, meaning that if you build quantum computers using superconducting technology, how can you connect to future quantum computers using optical link? That's extremely challenging task, but I will not talk about that. But it's a verification to explain why I'm working on both optic and superconducting system, because we want to develop both structures, and then connecting the two wavelengths is like the two subsystems in the quantum structures. So if you're looking at these topics today, I'll talk about the red boxes here. The green ones I mentioned is the motivation mainly, but all four boxes we are working on it, the technology is based on something which is extremely important, that's nonlinearity in quantum mechanics. A lot of technology we're developing is based on the nonlinearity, and they're really important because nonlinearity you can consider it as a quantum resource. And in principle, I love the quantum optic description. Sometimes we can bring up examples of four-wave mixing and two-wave mixing as the quite well-known types of nonlinearity in quantum optic. So where the quantumness really can coming out from this in terms of the application is really generating entanglement non-classical emission is one of the examples of using nonlinearity in quantum systems. So what I will do today for the four-wave mixing, I focus on optical domain, meaning that my talk will be in the few hundred terahertz. And then for the two-wave mixing, I'll switch the gear and go for superconducting system, which you can develop amplifiers much easier than optical domain. So let's start with four-wave mixing and what is the application. Again, this is I just very briefly explain about one of the main applications of this. And in fact, we're trying to build what we call quantum microscope. I do not talk about that. So in principle, you can use nonlinearity in quantum optic to develop microscope, a new types of imaging system to somehow, maybe in future, you can compete with the existing very advanced classical imaging system, which typically they have some challenges, like they're invasive, for example, if you're using X-ray for imaging, they have sometimes low resolution, they're slow and quite expensive. So in one of the efforts we do, we take in one of the crystals, we bite them, and then we inject light, a pump to this using the four-wave mixing. You can generate what we call hydrogen signal. There were some talks about that today. In principle, you can see this is a bulk crystal, is bulky. So when you're dealing with bulk, there's some good and bad things about the bulk. One of the big challenges about bulkiness is the signal either you generate, the photon pair generation is not so efficient. You pump the system with, I don't know, 60 milliwatt power, whatever you get out is not really, you don't generate a lot of photons. It's not efficient at all. So that will impact the future application. For example, if you want to develop what we call quantum CT scan system and try to make some images, the image is quite blurry if you're using single photon and coincidences in the hydrogen signal. So there are some ways to resolve this problem. Again, one of the main problem coming from the inefficient, the process you have, because the crystal you have is a bulk material, it has defect and a lot of imperfection. You can solve some of the problems, for example, by using the machine learning technique that we are developing in terms of the commercial aspect of this, but that's just a remedy. We don't solve the problem. We just have the data coming from the photon pairs we generated, which we don't have enough of them. We try to solve some of the problems using the machine learning post-process, but that's not the solution. So what is the solution? That's where now I'm talking about integration. So if you have the bulk and bring it down, make it smaller and smaller, you do the integration, like you make things smaller, so you have a lot of energy concentrated in a very small point. So based on that, most likely you can make the emission and photon pair generation way more efficient. So I'll talk about two topics nonlinearity in topological photonic insulators and in superconducting system. Again, both of them are, we have motivations for them. In future, we want to combine both of them for photon transduction. Let's start with the first part. For now, just I only talk about optical domain, 1550 nanometer, everything is telecom, so no superconducting system. Please don't be confused for now. So what is a topological system? Sometimes people are confused with topology versus geometry. If you're starting with that dot here, A, you're starting to deform it, and you have A, B, C, D, different geometries. You can see the geometry is changing when you deform the system. But then the topology of the system stays the same for all of them except for D. When you make a hole in the structure, you change the topology of the system, and the way topology changes is just really, I said, in a discrete manner. So you make a jump in the topology of the system when you're making a hole. I do not go through the entire topic of the topology versus geometry. We don't really need it, but we can really look at this property in optical domain. Topological system, for example, they have this sort of periodic band gap structure, and you can build them using different types of photonic system, integrated photonic system, using coupled ring resonators, photonic crystals, waveguide, and fiber. All of them, if they're coupled, you can building this band gap structure, and you can have topological system. Again, I do not go through the details. We don't really need this for now. So what is the important thing about this? Don't forget the problem. We have nonlinearity. We want to make photon pair generation or whatever we try to use more efficient. So we decided to have the bulk, make it smaller. We do the integration, right? That was a target. But then when you make the sample smaller and smaller in micro scales, you become way more sensitive to a lot of imperfection you might have in the system. Cracks, dust, fabrication, imperfection, all of them can affect the performance of your chip. How can you resolve that? So one of the properties of the topological system you have, they are robust against some sort of defects in the chip. Like if you build a photonic system, if you have a crack, most probably doesn't see the crack. It can just pass over, and then you still have the very good efficiency in the system. That's where we want to now combine nonlinearity in the chip we have with topological system, and then based on that, designing something, a chip, which can give you better like performance in terms of the photon pair generation. How can we do that? So the main goal here for me is combining topology with nonlinearity in a material nonlinearity we have like in silicon, for example. So what is the system we try to build? Just consider it's a micro ring resonator, 1550 nanometer. We have those resonators all coupled. I call this a unit cell. This unit cell doesn't have any band gap system. If you just couple them and then scaling up, you don't see any band gap structure. So something way more interesting happened. If you're starting to rotate one of them, making a kind of defect in sort of the coupling, now you can see it. You have two types of coupling in this unit cell. You have this coupling, I show that with theta A's, right? And then now you make this coupling different from the other three. So what happened when you do this and do the simulation, you can immediately figure out the structure has this band gap system periodically. And then I wrote some numbers here. Those are the churn number, winding number. Churn number is 0. So winding number is not 0. We call this Flickit topological system, but it has topological property. Forget about the Flickit, forget about winding number, churn number. What you have to learn here is, we have to learn here is this structure with this unit cell has some topological property. Okay, so then when you're looking at this band gap, you can see I have two black lines. Those are what I call them edge state. Those edge state, they don't talk to each other, but they exist in the band gap of the system. What are they? So I call this edge state. So there should be some edge that the state, it exists in that edge for the system. But where is that edge? So if I do the simulation, it's scaling up the unit cell, just copy and pasting and do the simulation. So if I now inject light in this corner, the light can propagate the edge of the chip, as you can see it. That's one of the modes. We had two edge states, two crossing. So where's the other one? If I inject the light here, depends on the direction you inject. you can activating this edge state. That's where you have two edge states. So what was the promise? The topological property allows me to really have some protection against some defect in the system. Can we see that in experiment? The answer is yes. So now let's consider I can remove one of the resonators. That's a defect. Let's say, I don't know, accidentally the chip is broken in that section. Can light propagates over? The answer is yes. So you can see a simulation predicts it goes over and then propagates again. So it seems like simulation somehow predicts this behavior. Can we do this experimentally? The answer is yes. This is the unit cell of the system. You can see it. We don't, in order to have this sort of defect in the coupling, we remove one of the resonators, but you don't need to remove it in principle. It's enough to not having the same coupling. So what you see is a silicon chip, including 300 ring resonators, all of them are coupled. It has a band gap system structure, and you can looking at the topological property of this. So how can we verify that? If I inject light here, it's only propagate the edge of the chip, indicating of having edges in the system. But then we notice about something way more interesting. Do you see that section? We have those lines here. That's a zoom in. That's a heater we have in the system. So when you're heating up one local point, what happened? You change the refractive index of the system. So when you change the refractive index, that's a defect. It acts like a defect. You want to simulate existing a defect. So we noticed about something very interesting. If you change the property of this heater, this heater enough, then you can trap light in a loop. So trapping light in a loop, that reminds you of something. That's a resonator. In a resonator, like a Fabry-Pro cavity, you have two mirrors. You can trap light inside. So now the topological property of this, this system allows you to trap light in a loop. So what happened? You create a local mode, a resonator in the system, using topological property. That's interesting. I can turn off and on this. I can switch sweep the resonant frequency, and depends where do you have the heater. You can activate multiple type of resonators, resonant modes in this system. So we call that flicker defect mode resonator, FDMR. So remember the FDMR because I'll use this a lot. Let's look at this. This is the camera we have. We looked at the chip in a very dark area. You can see the edge state exists. When we turn on the heater, we can trap light in the chip. So it seems like the experiment also immediately proved the existing of this FDMR. How can we look at the transmission? The transmission, you can see for red line, we don't have the heater on. If the heater is off, when we turn on the heater, we have very nice mode appear. Actually, the quality factor for this mode is better than bare resonator, like silicon resonator. If you just have a ring resonator coupled to waveguide, we have better quality factor approaching 10 to 5 for this chip. So can we see this like clearly? The answer is yes. This point is where I shine the laser. This is the wavelengths, and this is the chip under the CCD camera we have. What I do, I sweep the laser. When I hit the bulk, the middle of the chip shining up. When I hit the edge, the light only stays at the edge of the chip. Let's see if that really is the case. So you can see I'm moving the arrow. Now we hit the bulk. The entire bulk will shining up. And then when you go to the edge of the chip, it will stay at the edge of the chip. So clearly it has topological property, including the edge state. So this is the chip. Now we looked at the emission from the system. The main goal was combining nonlinearity in the system for wave mixing. And now I'm combining all of the what we talked about. We had four wave mixing in the system. We have topological property. Now we want to combine them and have it, and testing if the system really acts as it should. So how do we do that? We have the FDMR in the system. We pump the system in the middle. You can see it. We pump the system in the middle and then look at the signal and either in different FSR and figure out if we can measure the coincidence in the system. This is the result. You can see it. This is GSI, the second order correlation function with respect to time. We have a huge peak appears in the system due to the full wave mixing process in the chip. If this is a non-classical or not, we can define or violating Cauchy-Schwarz inequality using this equation, you can see gamma is way bigger than the age state alone. So it's a kind of indication of gamma is bigger than 1, indicating non-classicality. What about CAR? Coincident to accidental rate is a huge improvement compared to the age state. Seems like it works. But is this really non-classic or entangled? We looked at the entanglement emission from the system using Franz interferometry, and you can immediately see it when you split the emission to long and short passes. Depends on the phase you inject in the system. You can make the middle peak almost fully disappear with 97% almost visibility, indicating of having entanglement. Perfect. So that was silicon optic. Silicon is great, but the nonlinearity in silicon is weak. You don't have a lot of nonlinearity. That's a big challenge for optical domain. We don't have this problem in microwave system, superconducting system. What's the reason? Again, my field is it's a microwave optical transduction. We work in both areas. We want to have some defect-free microwave optical transducer for future. So that's where now we have to also learn a little bit about the superconducting section. My background, in fact, is superconducting, coming from mainly superconducting. Well, so that's where now you can talk about amplifiers, amplifications, and if we have some sort of types of physics also here. The answer is yes. In a superconducting system, you can get nonlinearity. Again, I love nonlinearity. You can get nonlinearity using artificial atoms you might build. So you can call that Josephson junction has huge nonlinearity, or you can get it from the materials itself, like silicon, for example, has some nonlinearity. In superconducting system, you might have some materials which they have nonlinearity. So in principle, why the entire concept here, it's really around amplification. Why do you need amplifiers in quantum systems and superconducting structures? That's mainly due to the fact that in microwave domain is low frequency. You have a lot of thermal noise in the system, and when you're dealing with those dilution refrigerator, you put your sample here, you have a lot of attenuators in the path. Like those are the attenuators, because you want to really get rid of the entire Johnson noise coming in and suppress entire noise to not reaching you qubit here down there. So, but then why do you need amplifiers? Because the emission coming from the system, it's extremely weak, like let's say from whatever microwave qubit you might have, superconducting qubit you might have, so you have to amplify the system using quantum limited amplifiers. So I call that quantum limited amplifiers, and amplification is quite central there. It's just not about amplifiers. Amplifiers, in principle, you can split them down in two types in general, degenerate and non-degenerate amplifiers in quantum optics. And for non-degenerate amplifier, you're dealing with two modes. This can lead to phase insensitive amplifier or two-mode squeezing or generating entanglement for many other applications. Or you can pick degenerate amplifiers, which both signal either they have exactly similar mode. That's what you call single mode squeezing. So this is a general definition. You can categorize amplifiers based on those two. So for example, degenerate amplifiers, they can give you phase sensitive amplification or single mode squeezing. Applications can be, for example, in LIGO. So learning from that, how can we do this in using Josephson junction? I just bring some examples. You can use single Josephson junction, for example, you have in the system to generate squeeze light and also amplify the signal. You can use the ring of the chain of the Josephson junctions, or you can using traveling wave amplifiers. The concept actually, we borrowed that from optic, which you have EDFA, erbium doped fibers. You have a fiber, you dope it with erbium, and then when light propagates over, you can get amplification. Similar concept exists. In the 2-pi, you have a chain of the junctions. Then when light propagates over them, you can building up the amplification, you have gain losses. So those are perfect, but they're very sensitive to a lot of imperfection you might have, a lot of heating, a lot of isolation, a lot of heating can, in fact, so affecting the performance of this Josephson-based systems. But similar to silicon, can we use nonlinearity in a superconducting system in gigahertz frequency and get amplification based squeezing? The answer is yes. How can you do that? You can use the materials like niobium titanium nitride. It's a kinetic inductance materials, and then you can build something very simple out of this. So what is the system? This is the resonator. You can see this ring, it's my resonator, working at 8 gigahertz, for example. So now frequency, I shifted from telecom to frequency, microwave frequency. And then when you have photons inside the system, you can get amplification because of the nonlinear property of this material you have. So we also have another resonator coupled capacitively. You can see that's a zoom-in resonator. So we have 2 resonators in the system. The ring is one of them, and then we have an L-shaped resonator in this side that's a zoom-in. So we have 2 modes. For now, I just focus on one of the resonators for now. So the first thing is you can tune the resonant frequency of this. That's a resonant frequency by applying just current in the system. So it's really tunable resonator. And you can use this to get amplification in the system. How do you do that? If you're looking at by solving the equations of motion and then looking at the full output of the system depends on 2 terms, like 2 brackets, you can see it. You have the A and A dagger, that's like a single mode squeezing the system and some noise up here in the system. And those are the gain factors for this amplifiers. Can we confirm the existing amplification? The answer is yes. This is the gain with respect to detuning. You can get up to near 50 dB gain in the system. Of course, it's a very narrow band structure. And you can change the property of this with respect to the phase. When you change looking at the gain, which depends on the phase, there's an indication of the squeezing in the system, but it's not exactly squeezing for now. We have to prove the existence of the squeezing. So another good thing about this is the gain with respect to the power, the saturation is way bigger than Josephson junction. For Josephson junction, typically the saturation happens around this point, but you can see it. We have near 30 dB improvement in terms of the saturation. That's perfect for the amplifiers actually you can use. So this was a single mode squeezing, but then we have more advanced. So for the single mode squeezing, we're using 3-wave mixing in principle. Now you have 2 cavities. We had 2 resonators, if you remember. The ring resonator and the L shape, they are coupled. One of them doesn't have nonlinearity. The other one, it does actually has, it contains nonlinearity 3-wave. So what happens if you couple the 2 systems together and they can hop photons? Can you have 2-mode squeezing or 2-mode amplification? The answer is yes. Just consider one of the resonators has this nonlinearity. That's a 3-wave mixing process. You have the pump in the system, and then you can generate either a signal at the same frequency. That's the generate situation I talked about. But then the photons can hop back and forth between the 2 resonators. Can we now see the amplification in both of the modes, which they are separate from each other? The answer is yes. So we looked at this behavior. One of the modes not tunable, the other one is tunable. We bring this mode in the anti-crossing point. When you park it in the anti-crossing point, you can exchange energy between the 2 resonators. Again, one of them is just nonlinear in the system. If you go to the collective, like the effective Hamiltonian, you can see the effective Hamiltonian for this system contains the single mode squeezing and actually some cross terms, which is 2-mode squeezing in the system. So it's very interesting. This coupled nonlinear coupled resonators, they can give you both single mode and 2-mode squeezing, depends on the detuning you have in the structure. So, and when you're looking at the amplification, you can see 4 bubbles appear. In the anti-crossing point, you have 2 modes, both of them showing the amplification. Bingo, the theory perfectly matched with the experimental side we have. What about noise? Compared to Josephson junction systems, we are really doing a very good job. We're adding near 0.3 quantum noise to the system. But the difference here is we can operate the system up to near 5 Kelvin. So that's something you cannot do it with Josephson junction. So it's a really high temperature. The system is resilient against the noise is coming from the temperature in the cryogenic system. So all of them, whatever I talked about for superconducting system, there is no indication of non-classicality. Where is the non-classicality in the system? We run the system into try to looking at the squeezing and entanglement this quantum system. So what we have here, in principle, we have again the ring resonator. That was where we can have the amplification. We have the nonlinearity in the system. Is the result really whatever we get? Is it squeezing or not? So squeezing here means we don't inject anything to the ports. we're in almost near vacuum, meaning that we cool down the system to 7 millikelvin. 7 millikelvin, if you're working at 8 gigahertz, you almost don't have any population left in the system. So you're really starting from vacuum. I mean, it's approximately vacuum, meaning that there is no input to the system, it's just vacuum coming in. So you're activating the system, you pump the system twice of the frequency, because that's a phase matching condition you have to fulfill. And then you're looking at the resonant frequency of this resonator and figure out if you have the squeezing or not. So effectively, this is a Faraday Pro cavity. Effectively, you can have a Chi2 materials, a three-wave mixing process. As I said, you can pump the system twice at frequency, looking at the output of the system and figure out if it's squeezed or if they're entangled. How do we do this? We put the sample in a cryogenic environment. As you can see it, we operate this at 7 millikelvin and looking at the emission coming out from this. So we do vacuum noise amplification. So the vacuum noise amplification, if you don't have a lot of noise in the chip, it can show you the squeezing or entanglement. So we have two modes. You can see it from both ports. We have the resonant frequencies, we can measure them. So we noticed about something. We developed the theory for this, look at the quadratures for the system. We have this quadrature squeezing appears for a just simple example. If the coupling to both ports are symmetric, meaning that if the etas are exactly half, we can ending up to this quadrature in the system. C here is the cooperativity. We define the cooperativity. And if C is 1, then you can reach 1/4. Below half, that's smaller than half. When you go below half, that means you have squeezing in the system. Let's see if that experiment can prove that. We looked at the violation of the Einstein-Podolsky-Barzanjeh based on this, meaning that you have two quadratures. You're looking at the variances between two. If that's smaller than 1, that's an indication of not only squeezing, but also the entanglement. So first of all, we looked at the quadrature for both of them. You can see it, we can go below half. By near 2 dB, squeezing is not a lot. With respect to the power, is this entanglement density? Yes, we can go below 1, indicating of existing entanglement in the system. And also we looked at the logarithmic negativity, another figure that you can really calculate. And based on that, you can verify if the state you have is it's entangled or not. So it seems like it really works. So what did we learn so far? I really try to explain, and nonlinearity is a very important resource in quantum optics in general, in quantum mechanics. You can use it for quantum sensing, as like imaging is one potential applications, but how do you really play with this nonlinearity to make it more efficient? That's something you can do a lot of work on it. I talked about the topological system for more efficient photon generation and also amplification and squeezing the macro domain using superconducting structure, mainly kinetic inductance amplifiers. So with that, thank you very much, and amazing work by my student who often really they do a good job to do this combining experiment from micro and optic, and then we slowly using those two systems for micro to optical transduction at high temperature, more than like higher than 1 Kelvin in principle for quantum communication, future quantum communication applications. Thank you very much.